Okay, today we're going to start talking about summation and sigma notation. This is going to lead us into the whole idea of finding area under a curve. But let's kind of backtrack a little bit. This is stuff that you've seen before, but you probably haven't seen it in a while. And when we talk about sigma notation and summation, we're talking about this. So sigma notation would be this. In general terms, right, that's the Greek letter sigma, which means sum. So we start with some variable, and we're going from 1 to n of a sub I. And all that means is this. That means I'm taking the first term plus the second term plus the third term all the way up to the nth term. Okay, so that's in general, that's what it means. You'll oftentimes see I, J, or K used here, and it doesn't have to start at 1. It can start at 0, it can start at 5, it can start at anything. So let me just show you a couple of examples. So one example would be if I start at 1 and I'm going up to 6 of I. And all that means I start at 1 and I'm going up to 6, and then I'm adding all of those together. Similarly, if I had sigma and I'm starting at 0 and I'm going to 5 of I plus 1, that's the same as saying 0 plus 1 plus 1 plus 1 plus 2 plus 1, right, all the way up to 5 plus 1. Okay, and then adding all of those together. So those are a few examples of what sigma notation is. Now we can do it with just single numbers going up by ones. The sequence really could be anything. It could go up by threes. It could go up by sevens. It could go up by anything, and it also doesn't have to be a linear kind of a format. Let's say, for example, I have I is 3, I'm going to 7 of I squared, right? Then I'm just doing 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared. Okay, and that's the idea behind that notation. So let's talk about some properties of summation. And these two properties are going to come in pretty handy. The first one is this. We have our sigma notation from I equals 1 up to n of some constant k times a sub I. And the idea here is that you can take that constant out and multiply it through at the end. So n I equals 1 of a sub I. So you would add up all of your terms and then take that sum and multiply it by that constant k. And the other property that's going to come in handy is that you can actually break up a summation into 2. What I mean by that is this. If I have a sub I plus or minus b sub I can actually do that as individual summations. So I can do that as a sub I plus or minus the summation of I equals 1 to n of b sub I. So those properties are going to come in handy when you're solving different types of equations. And so let me talk about kind of it's a pretty common example that comes up. You may have seen it in other sort of challenging problems, but here's the idea. If I asked you to find the summation of I equals 1 up to 100 of I. Now, you could sit there and do, well, 1 plus 2 plus, right, and you could do all of those out all the way till you get to 100. And that would be pretty tedious and pretty time consuming. Here's the idea of how we can sort of take that and come up with a summation formula for something like this. If I'm adding the terms 1 to 100, right, I can add them in that order. I can add them 1 plus 2 plus 3 plus, right, all the way up to 100. Similarly, I could add them in the reverse order, right? Addition is commutative. There's nothing saying I have to start with 1. So I could actually start with 100 and also go down by 1 each time. And if I added those two summation ideas, right, if I added those together, those two different formats, every sum would be 101, right? 100 plus 1 is 101. 99 plus 2 is 101. 98 plus 3 is 101. And if I get all the way down to here, it would also be 101 and 101. So every time I add those together, I end up with 101. Well, I know that I have 100 terms here, and I know that the sum of all of those is 101. So if I have 100 terms times 101, that would give me the sum of 1 to 100, but it would give it to me, right? It would give me the sum of 1 to 100 and the sum of 1 to 100. So to give it to me twice. And so what I need to do is divide that by 2 to actually get what that sum is. So this comes out to be 5,050. And if you think of it this way, you've got this 100 times 101 over 2. Well, isn't n 100? Right? So if you look at the basic format here, if n is 100, so that's the same as saying n. 101 is just n plus 1 over 2. And so I can actually use that as one of my summation formulas. If I'm just adding, starting at 1 and going up to whatever number that is of just the number, I can always use this formula. So if this was the summation of 1 to 20 of I, well, I could plug that in here, and instead of doing it out, so let me show you that up here. If I had the summation of I equals 1 to 20 of I, well, I can actually use this formula. So n is 20, so 20 times 21 over 2, right? And that would give me what that answer is. Okay, so that's the idea behind the summation formula that's already been derived, and there's several of them. I'm just going to give you the formulas. You don't have to know the derivations of them, but that's the idea behind that formula and where it came from. So let me give you all 4 of the summation formulas as those will be helpful to you when you're doing these types of problems. So summation formulas, like I said, there's 4 of them that will be helpful to you. The first one is just the summation of I equals 1 to n of some constant c, is c times n. Okay. The second one is the one we were just talking about, the summation of I equals 1 to n of I is just n times n plus 1 over 2. The third one is the summation I equals 1 to n of I squared, and that formula is n times n plus 1 times 2n plus 1 over 6. And the fourth summation formula is I equals 1 over n, or I equals 1 to n of I cubed, which is n squared times n plus 1 squared over 4. Okay, these are formulas that you're going to want to know. You're going to want to be familiar with them because they are going to come in handy for you when you're doing some of these problems. So let me show you an example of a summation problem that kind of uses a couple of these things. We're obviously not going to use all of the formulas in the same problem, but here's an example problem for you. And it says, well, the summation of I equals 1 to n, of I plus 1 over n squared, and that's for several values of n, for n equals 10, 100, 1,000, and 10,000. So we're going to do it at those 4 values, 10, 100, 1,000, 10,000. Okay, so those are the 4 values we're looking at that with. Okay, so I can start out by writing this as the summation of I equals 1 to n, and I can rewrite this as 1 over n squared times I plus 1. Recognize then that 1 over n squared, whatever n is, right, that's just a constant, so that can actually come out of the summation. So I have 1 over n squared, I equals 1 to n of I plus 1. Going back to our properties, right, we did just use the first property, now I can use that second property, and I can say, okay, well, that allows me to break up my summations. So I have 1 over n squared. The summation of I equals 1 to n of I plus the summation of I equals 1 to n of 1. Okay, so all I did was applied some of my properties. Now I have 1 over n squared, and this is one of the properties we were just, or one of the summation formulas we were just talking about. That's this one here. And so I can rewrite this as n times n plus 1 over 2. And this just comes out to be n. That's the same as this first formula here. It's just 1 times n, or n. And so then it just really comes out to be algebra, and cleaning this up a little bit. 1 over n squared is n squared plus 1 over 2, and then, n squared plus n over 2. I can rewrite n, right, as 2n over 2. And so I end up with 1 over n squared times n squared plus 3n over 2. If you factor an n out of this and then cancel your n's, you end up with n plus 3 over 2n. If you were to then go in and substitute those different values of n in, right, so we had 10, 100, 1,000, and 10,000, you can just substitute those values of n into this new formula. And we would end up with 0.65 here, 0.65, and then we'd have 0.515, then you have 0.5015, and then you have 0.50015. And as you see, as n gets larger, our sigma is getting closer and closer to 1/2. And so you could almost look at this as the limit as n approaches infinity of this is equal to 1/2. So that's the idea behind summations. Hopefully that'll help you out, and we'll see you next time. Take care. Bye-bye.